Here's our first example for three-dimensional static equilibrium. We've already talked about static equilibrium in detail, and you've known that in order for something to be at static equilibrium, the sum of the forces in the x direction has to equal 0, and the sum of the forces in the y direction has to equal 0. We've also talked about how to deal with vectors in 3 dimensions. For today's example, the only difference is going to be that we are going to add sum of the forces in the z direction equals 0. So we'll have 3 equations. For this first problem, you're given an object. It's a hook with a weight of 90 pounds suspended from it, as well as 3 connecting points to walls. Those are fixed connections. The fixed connections are at B, C, and D. You are also given a spring. The spring is a spring constant of 500 pounds per foot. Now, looking at our find statement, the only thing we are asked to find here is the stretch in the spring. In order to find that, though, we're going to have to be able to find the force in cable AB. At this point in time, I've drawn a free body diagram for this particular problem. You'll notice the only real difference between the free body diagram in this case and the given diagram is that I have labeled my unknowns. So I've got AB here, I've got AC here, I've got AD, and then I called this one down at the bottom where the hook was and the weight AZ, and that I've replaced what was initially a spring with just a force. We're actually going to deal with that force later in the problem, so we'll come back to that later. Now, just as a quick refresher on the way that I draw these free body diagrams and the way you're going to see notation in this class, AZ and AB are both drawn along the axes. So AZ is strictly a z vector, AB is strictly a y vector. You'll notice that AD has 2 extension lines drawn from it, indicating that it is on the xy plane. There is no z component for AD. Likewise, AC has only 2 extension lines drawn from it, indicating that it is on the xz plane, hence there is no y component. Now, the actual math to do this is very simple. We are simply going to apply static equilibrium to each of the 3 respective coordinate directions. However, before you start, it's really a good idea to stop and think about how many unknowns are in each direction. So typically I start with the x direction just because my mind works x, y, z. So let's look at the x direction. How many unknowns do we have in the x direction? There is no x component for AZ. Likewise, there is no x component for AB. AD has an x component right here, and AC likewise has an x component right there. So how many unknowns do we have? We have 2. We do not know ACX, we do not know ADX. So let's look at the y direction. AZ has no y component. Likewise, AC has no y component. AD's y component is right there, and AB is only a y vector, so that's y component right there. There are 2 unknowns in the y direction, so that is ABY and ADY. Now let me just pause and say, earlier remember I said you need to have at least as many equations as you have unknowns. It is possible for us to end up with 3 equations and 3 unknowns in a 3-dimensional system and still be able to solve it. However, before you just sit down and say, okay, I'm going to start with the x direction or y direction or z direction, look at all 3 directions, because many times one of them will be of greater help, and that is definitely the case here. Look in the z direction. AB has no z component. Likewise, AD has no z component. AC's z component is right here on the z-axis, and AZ is only a z vector. So there's 1 unknown in the z direction. So that'll leave us with 1 unknown and an equation that we can solve. So I'm going to start with applying static equilibrium to the z direction. So the first thing we need to state is the sum of the forces in the z direction equals 0. which means that 0 equals plus or minus AB Z plus or minus AC Z plus or minus AD Z plus or minus AZ Z. Looking at our vectors, AD has no Z component. Likewise, AB has no Z component. So then 0 equals. Now you are no longer required to write your where statements. If you still prefer to do so, you may, but I'm going to skip that, first of all because I'm out of space, and second of all because I don't feel it's necessary here. AC's Z component is a positive 3/5 times AC. Next is AZ's Z component. AZ is a negative AZ. It's the full value of the vector. So solving for this, AC equals 5/3 times AZ, which means AC equals 5 divided by 3 times AZ was 90 pounds. And that leaves us with a positive 150 pounds. Now keep in mind that you are required to include a sign here. Okay, the sign indicates not that AC is in the positive Z direction, because it's not a Z vector, but that the sense of that vector agrees with what we assumed. Something I didn't mention earlier is that all of these vectors, AD, AC, and AB, are assumed vectors. We were not given vectors initially. We just assumed their directions. Our assumptions could be correct or incorrect. In this case, it happens that my assumption is correct. So I can now continue. We have found AC. We have found it to be positive 150 pounds. At this point in time, there are two other directions we could go to. So let's go ahead and look at the x direction. In the x direction, AB has an x component that we don't yet know, and AC has an x component. We've already found AC, so we can solve that. So that's where I'll go next. Just to look at something here, we can't go to the y direction next because I don't know AD's y component yet, and I don't know AB's y component. So the next step, which in this case is step 3, is applying static equilibrium to the x direction. I also want to say that every time you do one of these problems, it's going to be different. Every time you do a three-dimensional problem, you may have to do a different order. So in this case, I started with Z and then I'm going to go to X. Sometimes you might start with Y and then go to Z. So it's going to be different every time. You just need to look at how many unknowns you have in each direction. So sum of the forces in the X direction equals 0. 0 then equals plus or minus ABX plus or minus ACX plus or minus AD plus or minus AZX. Now at this point in time, I'm going to look and see if any of those have a 0x vector. and AB has a 0x component, and AZ has a 0x component. So now our next statement. AC's x component is a negative 4/5 AC. AD's x component is a positive sine 30, or I'm sorry, sine alpha times AD. So solving this for AD, would give 4/5 times AC over sine alpha. So AD equals 4/5. Now when we plug the value in for AC, it was a positive value, but I'm going to include the sign here because it is non-trivial. The sign must come with any vectors that you solve for, okay, any assumed vectors, because that sign indicates whether you're correct or incorrect. And that is going to equal a positive 240 pounds. Last but not least, we're going to take a look at the y direction. So this is step 4. Applying static equilibrium to the y. So we'd say sum of the forces in the y equals 0. So 0 equals plus or minus AB, y plus or minus AC, y plus or minus AD, y plus or minus AZ, y. Now some of these do not have y components. AZ does not have, or AZ does not have a y component. Likewise, AC does not have a y component. So then 0 equals, AD's y component is a negative cosine alpha times AD, and AB's y component is simply a positive AB. So AB equals cosine alpha times AD, and AB equals cosine 30 times AD, and AD was once again bringing the sign along, a positive 240.000 pounds, which equals, means that AB is a positive 207.846 pounds. So at this point in time, we know the value of the force in AB. What we still don't know is the stretch in the spring. So that's what we're going to solve for last. And as you recall, F equals K times S. The force here is AB, so that equals lowercase k, the spring constant, times S, which is the stretch of the spring. We know AB, it was 207 pounds. We know K, it was 500 pounds per foot. We don't know S. So we rearrange this equation to say S equals AB divided by K. So then that's S equals AB is 207.846 pounds. K was 500 pounds per foot. And then after we do that, we find that S equals 0.415692 feet. So the final answer is S equals 0.4157 feet. So that's it to do static equilibrium in 3D. It's not that much harder than in 2D, with the exception that you have one more direction.